Thank you very much for the invitation. It's great to be here. Uh, can you hear me okay? Okay. So the talk today has to do with almost disjoint families in models of AD+. And so, sorry, no mice creep into this talk. They'll come in waves next week. Let me just start with some background. So this is joined with William Chan and Steve Jackson. And so the general kind of topic for this would be the study of almost disjoint families on cardinals kappa in natural models of AD+. And so the kind of, this should be construed as sort of a test case for this hypothesis that AD+ has a very robust structure theory that decides, amongst other things, all natural cardinal characteristics on the region that it influences, namely on all kappa less than theta. And so you can vary this topic by replacing almost disjoint families by things like independent families, reaping families, things that you learn in your cardinal characteristic classes into this. And so the kind of the theme is that you cannot change these characteristics by forcing over models of determinacy, preserving determinacy. So there's some evidence for that, and one of some of it is in this theorem, namely that you start with AD+, you have a set forcing that is a surjective image of the reals, then AD+ must fail. In the generic extension, and so this is not the end all and be all theorem, because you can say, well, what if I have a bigger forcing or something? What do you do? And so we don't know that such forcings can preserve AD plus or not in general. So the kind of the conjecture here is that if you take any set forcing that adds a real, then AD plus must fail. That's the kind of the sort of the final theorem in this direction. I'm sorry. Yeah. Okay. Oops. Okay. So let me define almost disjoint family. So we study. So we take kappa to be an infinite cardinal, and we consider kind of two different ideals: the bounded ideal B kappa and the P kappa kappa, which is the ideal of sets that are subsets of kappa and have cardinality less than kappa. And so you can consider a family that is called I almost disjoint relative to some ideal I on kappa. So we only care about, in this talk, ideals I that it's one of these two guys. Okay, but you can define this for any ideal, such that whenever you have two distinct members of A, the intersection is in the ideal. Okay. If kappa is regular, then these ideals are equal, so they don't. It doesn't matter which one you consider, right? But for singular, the situation is less clear. Okay. So I'll say more about this later, but that's the setup. What happened? Do I have to point back to this place? Oh. Okay, so let me start by kind of introducing some, or just going through some basic, some history of why we consider this kind of problems. So in their paper, Schrittesser and Tornquist resolved a question by Matthias. It's a long-standing open question concerning mad families on omega. And so what they showed is that if you have DCR, the Ramsey property, and something called the Ramsey almost everywhere uniformization principle, then you can show that there are no maximal almost disjoint families on omega. And so I'll say more about these later. We're going to generalize this kind of theorem. And these are consequences of 80 plus. And in kind of a similar development, Neiman and Norwood also showed the non-existence of maximal almost disjoint families on omega under 80 plus. And their proof is more kind of the 80 plus flavor that you know from this conference than what Professor and Tornquist did, which is more combinatorial. And Sandra asked the authors, well, actually she asked William whether you can have maximal almost disjoint families on omega under 80 plus. Sorry, on omega 1 under 80 plus. And so we were kind of sitting around considering these problems for some time, and with respect to one of the ideals that I defined earlier. So it would be the bounded ideal on omega 1 or the p omega 1 omega 1 ideal, which is the same thing. Okay, so here's some results. So you can show that there are no maximal almost disjoint families on omega 1, and then that has something to do with, then you could get something like the failure of the Caripa hypothesis on omega 1. And more generally, you show that under 80 plus, if you have a cardinal kappa less than theta of cofinality bigger than omega, then every B kappa or P kappa kappa almost disjoint family has to be waterable. And furthermore, there are no mat families A such that the cardinality of A is greater than or equal to cofinality of kappa. Sorry, this is kind of, it's phrased kind of weirdly. I mean, so the furthermore clause, just say it again. Furthermore, there are no mat families such that the cardinality of the family is greater than or equal to cov kappa. So I'll say more about this when I kind of go to the results. So these are not necessarily equal now, right? I mean, these ideals are going to be different if kappa is singular, right? So you got to consider kind of these two cases separately. Yeah, you can take you can partition kappa into less than cov kappa many pieces. So that's kind of trivially a mat family, but it's going to have cardinality less than cov kappa. And so these are all kind of less than cov kappa, they're kind of these trivial mat families. But what we're saying is from cov kappa on, there's no such thing. And so the first clause is also kind of important here because remember we are in the 80 plus context. So you have to also consider families that are not waterable, right? And what we showed is that any such family you can't have non-waterable map families, period. Okay, and then there's the cov cap omega case, which is the harder one. So what's happening at the cov omega? And it turns out that we can only do it for one of the ideals, namely the bounded ideal. And so you can show that there are no map families on kappa, which is cov omega. But with respect to B kappa, which is the bounded ideal on kappa. And the proof runs into trouble if you're trying to adapt it to the P kappa kappa ideal. And so I'll show you the proof a little bit later, and you kind of see like clearly it's not going to work if you're trying to deal with the other ideal. And of course, if you are in the ZFC context, then there are kind of non-trivial mat families, and you can in fact force the existence of mat families, say on things like Aleph omega. that are even have different cardinalities, and so I should have done a better literature review here, but when I looked at papers on ZFC, math families under ZFC context, then the earliest account I can find was some paper by Erdős and Heckler, where they were considering math families on Aleph Omega and possible values of math families on Aleph Omega. So they were talking about forcing, well, maybe not forcing, but possible values of math families on Aleph Omega. And so in the early 2000s, Shellac and some co-authors have shown that you can force like a spectrum of values for math families on Aleph Omega. So it's consistent that there are math families of a spectrum of cardinalities relative to large cardinals. And they all consider the families relative to the ideal P kappa kappa, so P Aleph Omega, for instance. And I couldn't find any literature that deals with families on the other ideal or any other kind of ideal. So the bounded ideal, for some reason, was not considered, and so any questions so far? Okay, so let me deal with the cofinality uncountable first. So there are some basic facts from 80 plus theory. Let me just kind of discuss them. So it's easy enough to show that there are math families relative to any of these two ideals for any cardinal lambda less than cov kappa. So that's kind of what I just said. You split kappa into lambda many pieces, partition kappa into lambda many pieces, each of which is size kappa, and then that's a math family. For any kappa, there's no math family of size cov kappa, and that's just diagonalization. So you can diagonalize. Oops. And this one is a little more difficult. I'm not going to say the proof, but this is a kind of a combinatorial thing that we need for the proof. So if you take an ordinal kappa, in fact, and you have a map from the reals onto P kappa, then you can find a countable set, script E subset of P kappa, and a comeager subset C of R, so that this script E set consists of pairwise disjoint subsets of kappa and covers all of kappa. So it's a countable partition of kappa into, partition of kappa into omega, or countably many pieces. And the C here is a comeager subset of the reals. And for any x in this comeager set, you can find a subset F of E. Yeah, this should be a script E, sorry. So that the value of phi of x is exactly F. Sorry, not F, but the union of F. This should be a union of F. And I mean, I'm not going to say the proof, but the proof basically uses kind of this 80 plus fact that the meager ideal is infinitely additive. So any Walter sequence of meager sets, the union is meager. Yeah, I mean, it's yeah, just that, yeah. And there are two more things that we need. For any kappa, I'm not sure what, yeah, I think it got cut off here. I think math over leaf timed out on me, and so for some reason it doesn't render the rest of the sentence. Okay, let's skip fact 4. Let's go to fact 5. Damn you, math over leaf. It's a free prescription, so they do this to me. Okay, so we're going to use fact 5 as well. So 80 plus implies that, so this is kind of what I said. It implies that if you have a a set X, which is a surjective image of the reals, then either X is valuable or the reals inject into X. That's a Wooden's dichotomy theorem. So that's an 80 plus. And so how do we use these kind of things to prove this? I'm going to just show the first clause. The second clause is a little more technical, so I'm not going to say much more than this. Just the furthermore clause is just going to be a little more elaborate diagonalization argument. It's not too difficult, but it's a little annoying, so I'm not going to do that part. So this one is more interesting. So let's take a family A that's almost disjoint. And if I'm giving you an injection from the reals into A, so we're trying to show that this family is valuable, and so suppose not, then by Wooden's dichotomy theorem, it has to be, there's a copy of the reals in it. So this injection injects the reals into it. So by this fact that I mentioned before, so you can find a countable set, basically a countable partition of kappa and a comeagre set C that for any x in the C, phi of x is the union of some subset f from E. So that's what this thing says. Okay, so you look at any x in this comeagre set C, the value of phi of x, which is a member of the family, is the union of countably many things from E. Okay, E is countable itself, right? But you can kind of find a countable subset of E that unions up to phi of x. And then you let E prime be the ones in E that have full cardinality. So that's a countable set as well because E is countable. And so given any E in this E prime, just look at the set X in C such that the E is there are too many E here, sorry. The Roman E is a subset of phi of X. So given any E which is full cardinality, given any Roman E of full cardinality, look at case of E, which is the reals in this comeagre set that such that phi of that real covers the set E. And since E prime is countable, there's got to be some Roman E such that the set case of E has at least two members, right? To just pigeonhole, basically. Well, you take any, again, this is the rendering here is not. So take two members of KE that are distinct. So this should be different. X not equal to E. Then the set E is contained in the intersection of phi x and phi y. But remember, E has full cardinality, so it's again, sorry, this should be. So basically, we showed that you take any set X and Y in KE, then this E is by definition is contained in the intersection, but cardinality of E is kappa, and so this means that phi x and phi y cannot be almost disjoint by any of these measures, by any of these ideals, right? Anyway, so the key point is you kind of the existence of this script E here, and the fact that you can do it, you can cover a large subcollection of the reals, namely a comeagre subset of the reals by kind of a countable set here is kind of the key part of this argument. Okay, so just some remarks. So So as I said before, the furthermore clause generally is just another diagonalization argument, but you can kind of already see it that it must be true in the case where kappa is regular, right? Because of both phase GCH. If you have kappa being regular and you have if you give me any subset of P of kappa, and if it's valuable, then it cannot have size bigger than kappa. That's both phase GCH. Right? So the furthermore clause. So here's the theorem, right? So in the case where kappa is regular, cov kappa is kappa, and so you can't have any mat family A that has cardinality greater than or equal to kappa. Right? You can't have a mat family of cardinality kappa by diagonalization. So you cannot have a family of size kappa plus or more by both phase GCH. Okay, so that's the I'm not gonna do the singular kappa case here, but it's again it's gonna be using both phase GCH down at cov kappa and some diagonalization tricks that you use to get it to work. In the case where you want to deal with say kappa at least theta, then you have to assume that your model is a natural model. LP of R, because otherwise you can monkey with the power set function above theta, and you don't have a definitive answer. But generally speaking, you can, for example, if you take kappa to be regular, at least theta, you can build a mat family in hot, mat family on kappa in hot of size kappa plus, and remember kappa plus of hot is kappa plus for kappa. At least theta. And so you take that mat family in hot of size kappa plus, and you show that it actually is maximal in V just by analyzing the Vopenka algebra. So the key is the Vopenka algebra is theta CC. And so you use that to show that the family remains maximal. But you cannot do this for some other family. So for example, you take independent family on kappa. So you can think that you can try this trick again. I don't see how to do it. You take a maximal independent family of size kappa plus on kappa in hot, and you're trying to show that it remains maximal in your determinacy model. I don't see how to do it. So there's some surprises if you vary this problem. Because the quantifiers kind of all get messed up. Yeah. So that's the situation with. So there's a sort of a complete answer to this question about mat families on kappa above theta in these natural models of 80 plus. I mean, it's in the paper. I just kind of give you one case just to have the flavor. Basically, you just take your mat family in hot and then show that it's maximal in V. That's all you do. You take the, it's in the, it's in the ZFC model. You have a maximal family, and you just take it and you show it's maximal. And the key is that you have to assume this is a natural model of 80 plus. So in that case, then hot computes successors correctly above theta. Okay. All right, so let's go to the, how much time do I have? Okay, great. So let's go to the cov omega case. So I need a couple of definitions. So, so let's take A to be a subset of omega brackets to the omega, and S is a finite sequence such that max S is less than min A. Then you associate with S and A kind of a basic open interval, in this Allen-Tuck topology. So NSA is the set of S adjoin G, adjoin G where G is in A. So a set X is Ramsey null if for all S finite sequence, and RA should be a subset of omega to the omega with max S less than min A, then you can find an infinite subset B of A such that the basic open interval NSB is disjoint from A, is disjoint from X. Okay, that's Ramsey null, right? So you take any basic, you take any A like this, you can shrink it to infinite B so that the interval NSB is disjoint from this X, and it's co-null if the complement of it is null. And Ramsey uniformization, so this is one of the hypotheses that Schittiser and Tornquist used in their paper. And so, yeah, I'm going to define it for omega, but it makes sense for kappa, for uncountable kappa as well. So I might as well, I didn't write it this way, but let me just say it like this. So uniformization for omega, Ramsey uniformization for omega is a statement that for all relations R subset of omega to the omega across P omega, there is an infinite set A and a function P from domain of R intersects A to the omega to P omega, such that any F in the domain of R intersects A to the omega, the relation R holds for F V F. So that's the Ramsey uniformization. So you can uniformize a relation R on omega to the omega across P omega on basically a Ramsey co-null set. So this function phi is the uniformization for the relation R, and it's going to uniformize it on a big set. Not necessarily everywhere, but on a big set. Okay. And a basic lemma here, you have a, I don't know, I didn't see this thing written anywhere. So our, the paper have this proof. Besides our paper, I guess. So you assume AD plus, or more precisely AD plus DCR, the Ramsey property, omega arrows omega 2, and Ramsey uniformization for omega. You take any kappa, which is an ordinal, and you have a sequence X alpha of length kappa, which is a sequence of Ramsey null sets, then the union of the X alpha is also Ramsey null. So it's kind of a analog of the, for the Ramsey ideal, this is the analog for the, this is infinity additive for Ramsey ideal. So it's the analog for the infinity additivity of the meager ideal. So you can show this under AD plus. In fact, you just need these hypotheses here. And I should say before I forget, you can define Ramsey uniformization not only for omega, I mean but it makes sense for kappa as well. For any uncountable kappa, you just change the second omega here to kappa, and this omega here for kappa, and everything else is the same. Oops. Yes. So yeah, you right here. The following theorem is a theorem of AD plus, and it kind of generalizes Matthias's well-known result on continuity for functions from omega to the omega to the Cantor space. So if you assume sorry, Gabe. I think that's not what I. This is the continuity result, and then Ramsey uniformization. I have it later. So you can prove two versions of continuity for functions from omega to the omega to kappa. So the first version is you just have a function from omega to the omega to kappa. The second version is omega to the omega to 2 to the kappa. So this is kind of the generalization of Matthias's result. So the first version gives you that on a big set, the function phi in fact is continuous in the sense that there's an infinite subset B of omega such that phi restricted to, yeah, this should be restriction, I'm sorry. Again, it doesn't render correctly. Phi restricted to omega, B to the omega is continuous in the sense that if you take any function from B to the omega, then there's a natural number n such that for all G in B to the omega that agrees with F up to n, the values of F and the values of phi on F and phi on G are equal. So it's the same order. Okay, and then you can do the same for functions to the 2 to the kappa, but you get a little bit weaker continuity. So you get that any function F in B to the, so there's some infinite B, and such that any function F in B to the omega for any kappa, for any alpha in kappa, there is some n such that for all G that agrees with F up to n, the values of F and G, phi of F and phi of G on alpha are equal. So here I'm thinking of phi of F and phi of G as functions from kappa to 2. So these guys are either 0 or 1. So phi of F of alpha and phi of G of alpha are the same. And so it's 0 or 1. And then later on, I guess I'm going to make it more confusing by identifying these functions as subsets of kappa. And you get a corollary that's basically it's an analog of one of these facts that I stated earlier from this kind of continuity. So I'm not going to prove this. I mean, it's kind of technical partition type argument. But you also get this analog. So if you have a function phi from omega to the omega to p of kappa, then you can basically cover it by a countable set, just like before. So there's an infinite B and a countable E such that E consists of pairwise disjoint subsets of kappa. The union is kappa. And you take any function F in B to the omega, there is some subset of E. Again, this should be script E here. So that phi of F is union of F. Right? So any phi. So on a Ramsey large set, the function phi is kind of covered by this countable set here, basically. And remember, this is what we used earlier to prove the theorem. And so again, just to kind of stage Schrittesser and Tornquist's theorem in the more proper context, assume DCR, the Ramsey property, and Ramsey uniformization at omega. Then there are no infinite math families on omega. So omega here obviously is regular, so these ideals are equal. But now when we're trying to generalize this theorem to some kappa of cov omega, we can only do it for the B kappa ideal. Sorry, this should be P omega omega here. And so that's kind of just to remind you. Yeah, okay. So sorry, Ramsey uniformization at kappa is a consequence of AD plus. I guess I didn't state it up there, but you can prove that. Okay, so what we need more than what they need because this kappa here is bigger. So we need AD, DCR, the Ramsey property, and Ramsey uniformization at kappa. And remember, kappa is some uncountable cardinal below theta of cov omega, right? So the theorem is, you show that, the theorem is that, the conclusion is that there are no map families on kappa relative to this B kappa ideal, the bounded ideal in kappa. We don't get it for P kappa, but you get it for B kappa. And so let me, yeah, so that's about time. I have 10 minutes, so I can outline the proof. All right, so the first step is you fix a cofinal function from omega into kappa, increasing and cofinal. So rho is a cofinal increasing sequence from omega into kappa. And you first kind of split the family script A into two parts. The first part is just the first omega, or however you want to do it. There's going to be omega many distinct members of the family. So you kind of just pick omega many of them, and then the rest is going to be into the other slot. So that's the AN. So there's just the first some omega many members of the family. And so you define this basically diagonalization set here. So there's some diagonalization going on. So for ij, I less than j less than omega, eta ij is the least eta in a sub I, this guy right here, that is bigger than rho j, and it's not in the union of the previous set. So let me draw a picture. So you have your AI here, and you have your AJ. So all the AIs are enumerated. So you got your eta IJ. So it's gonna be so here's kappa, and then you basically your function rho is a function from omega cofinal and kappa, right? So your eta ij is just some member of AI that is bigger than this rho j here. Okay, so something. I mean, you know there's such a thing because AI is an unbounded subset of kappa, and so you can take the least one if you want. And so that's what we do. We define eta ij to be the least eta that's bigger than rho of j, and it's not in any of the previous am for m less than I. So you can do that because of the assumptions, right? The point is the okay, and then you can take bf to be the collection of the eta fn plus 1 for n less than omega. For any f as increasing functions from omega into omega, you associate with f this set bf, which is this set right here. So it's going to be an omega sequence, an omega subset. It's a subset of kappa of size omega, and it's going to be cofinal in kappa. Okay. And then we're going to define a relation on omega to the omega cross p of kappa by defining RAF holds if and only if A is a member of the family and A intersects BF is unbounded. So this is where we're going to use the previous theorem. So you shrink omega down to C0 and let phi be a function that uniformizes R. So that's using the Ramsey uniformization at kappa that we had before. That's a consequence of 80 plus. And then you further shrink C0 to C1 so that this function phi is weakly continuous. And so you kind of do it in two steps. So you're gonna shrink it so that this uniformization function of this relation is weakly continuous on some infinite subset C1 of omega. All right. And then and you can show that this function is not constant on C1. So this is kind of just a calculation. And so so what happens here? Well, now first, so now we're going to use the continuity here. So you take two functions f and g that are distinct so that phi of f and phi of g are distinct. It's not constant, so there are such functions, f and g like that. And because this function phi is weakly continuous, there is some alpha such that because these things are different, so there's some alpha, take the alpha star to be the least one such that the values of phi of f and phi of g differ at alpha star, all right? And then because the function phi is weakly continuous, you can find finite sequences S0, T0 such that whenever f prime and g prime extend S0 and T0, so sorry, this should be S0 and T0. So here's S0 and here's T0, and whenever you take f prime g prime in this infinite set C1 in the set C1 to the omega that extends S0 and T0, then the values of f and f prime, phi of f and phi of f prime at alpha star are equal, and the values of phi g prime and phi g at alpha star are equal. So that just follows from weak continuity, okay? And hence they are different, right? These guys are different, all right? And then this is the last slide, so I'm almost done here. So you have S0 and T0. Now you're gonna inductively define sequences Sn, Tn, and delta n with the property that the Sn plus 1 extends Sn, Tn plus 1 extends Tn. The delta n are kind of cofinal in kappa, so in particular I want them to be bigger than rho of max Tn. And the key property here is that whenever you extend Sn plus 1 and Tn plus 1, so take any f prime and g prime extending Sn plus 1, Tn plus 1, delta n is inside of this inside of the intersection. So you kind of just keep extending. Basically, there's some inductive thing going on here, right? So if you have Sn and Tn, you can kind of use weak continuity and some partition relation to extend it to Sn plus 1, Tn plus 1. So you are kind of in these good intervals in the sense that you know whatever you extend past S0, T0, the values of phi on these two sets are going to be distinct, right? Because it's witnessed by this by this thing right here. So by continuity, anything that extends S0, T0 would have to be different somewhere, and at this location actually. And then so you can so that's good, but then you can inductively define these sequences of finite sequences Sn, Tn in such a way that the further you extend, the more you have in your common intersection. In particular, the delta n's are in the intersection of anything that extends Sn plus 1 and Tn plus 1. Okay, so what are we getting from that? You're getting that if you take f to be the union of the Sn and g to be the union of the Gn, the phi f and the phi g, sorry, phi f and phi g, when you intersect them, you have to contain the full the sequence delta n. And the delta n sequence is cofinal in kappa. So you violate the fact that this family is a B kappa, almost disjoint family. And so that's a contradiction. And so, sorry, I lied. I mean, there's one more slide, but it's just collecting a bunch of questions that I had before. So, but just one last remark. You know, you can sort of see that this is a construction that only lasts omega many steps, And that's why it only works for the B kappa ideal. If you're trying to do it for the other one, P kappa kappa, it's not going to work. So. And so there are 3 questions that I had before. So can you do it for P kappa kappa? If you forced to add the reals over a model of 80 plus, must you kill 80 plus? And what can you say about other types of cardinal characteristics of this?